So of course a major problem in general when recording video is that I do not hear myself until I am done recording, and apparently I had the microphone amplifying my sound too much. So I hope I'll put a note so that I hope that I'll even say in the email that the first part of the lecture is extremely loud because it hurt my ears. Okay, so what we will try to cover basically, or what we will cover, is that we are going to talk about scheduling for multiple environments. Tomorrow's lecture in class we will talk a bit about some queuing theory. This is a very mathematical discipline, so I actually prefer to have it outside of the lecture, outside of the video lecture. So and then there's we'll talk a bit about overload management and a case study also again tomorrow in the lecture. In this video lecture, we'll basically cover scheduling for multiple environments and different scheduling algorithms, and we'll take a deeper look at how scheduling is done in the kernel, with of course code snippets. So we will cover the whole chapter 7 as a whole, so you should basically read the whole chapter. So scheduling. Let's start before talking about what scheduling is to talk about what a workload is. And the workload is basically a set of tasks, jobs, threads, processes that need to run on the processor, or that need to access to some resource. Basically, it's typically the processor. But it can be the I/O devices also. The workload description includes not just the number of tasks, but also when does the task arrive, because that can make a difference. Two tasks arriving in opposite order, reversing order, can make a huge difference in how you do the scheduling. And how long or how many cores or cycles does it need to compute whatever it is supposed to do, not cores but cycles, because each task will have its own profile, basically requiring some resources different from other tasks. We would like to build a scheduler that works for multiple applications and multiple environments, not just a single application nor a single environment. So not just right now you have implemented your syscall. Some of you have showed me the results on both the ARM processors, which you have in the Raspberry Pi and the Raspberry Pi 3s, but also some of you have shown me their code in virtual machines and on desktops. There are things that you need to consider when building a scheduler. Is that the workload can be either compute bound, so it can be basically in deep need of memory, deep need of CPU. Sorry, it can be memory bound, which basically means that you have to communicate a lot with memory. Typically, you might also need to communicate with the disk, but that's different. And I/O bound. And I/O bound in the book and in many operating systems book, they include memory bound applications because they need input-output from outside of the CPU. But when you talk about softwares in general, I/O bound typically means that you need to access disk or access something that is outside of the memory architecture too. There is also the notion of network bounded softwares, but these are again can fall within the I/O bound application category, but they are applications that basically, like BitTorrent for example, that needs to download a lot of things from the internet. So a scheduler is called work conserving when basically the scheduler output never makes the processor idle when there is work to do. So of course, if there is no work to do, if there is nothing to do, then the processor will be idle because, well, there is nothing to do. But if there is anything to do, then the processor should not be idle as long as there is more stuff to do.